Section 8.3 is about hypothesis testing for a single mean. And I set up these notes so they really mimic 8.2. I guess to the extent that I could, I tried to make them look similar, just to kind of emphasize that the procedure is really similar. I think if you can do one of them, like if you can do a test for a proportion, you could do a test for a mean, and vice versa. The only things you have to keep straight maybe would be what distribution you have to use, because how for a mean you'd use the t-distribution, not the standard normal. Other than that, the way that you check to see if you have a large enough sample size is a little bit different, because for a mean you just need n to be at least 30, or I guess you need the population to be normal, one of the two. If the population's normal, you could have a sample size of 4 and you'd be good to go. But other than that, I mean, yeah, it's about a mean instead of a proportion, so the hypotheses are going to have mu's in them instead of p's. But the way you'd figure out what kind of inequality you need in the alternative hypothesis, that's exactly the same as it would have been for a proportion. But I mean, yeah, there are little things that have to change just because it's a mean instead of a proportion. But the general setup for what you would do in a hypothesis test is going to be pretty similar. All right, so let's see. There should be a mu, since this is about a mean, and then mu 0. So like it says here, mu 0, that's just some number. Which that'll be specified somewhere in the wording, right? We're looking for evidence that the population mean is greater than 10. Then your mu 0 is 10, right? That kind of thing. And then we do have to use students' t-distribution with n-1 degrees of freedom. And this is going to be the correct distribution when the population standard deviation is unknown. Our book, and this is a very common thing for textbooks, basically all of them do it, they'll first say, well, if you know the population standard deviation, then you could use a standard normal distribution. That's true. You're never going to know the population standard deviation in real life. Because in order to know that, you would have to know what mu was, right? Because the computation of sigma is based on knowing mu, right? It's the average distance from the mean. You have to know what the mean is to make that computation. But then, if you knew what mu was, there would be no point in doing the hypothesis test, right? It would just be, oh, mu is this number, that's that. So it's not realistic. So the realistic one is not knowing the population standard deviation, and so that's what we're going to do. And then there's our test statistic, that last bullet point. So the x bar minus mu 0 over the standard error, s over the square root of n. So if you're going to grind it out by hand, the computation for a mean actually isn't that bad, because you don't have that big root in the denominator anymore. But I think what most people are going to pick is this down here at the bottom of the page, to do it with StatCrunch, because then you don't have to do any of the algebra, because StatCrunch will do all of it. So stat button, you go to t-stats, and then one sample, and then for what we're going to do, I think it's almost always going to be with summary. I think there are ones when we get into the next chapter. Like I think there are ones in chapter 9 where we end up using with data. But for right now, we're just going to be using with summary. So the summary values are like if you have x bar and you have s, those are summary values. I guess if you had like a spreadsheet or a CSV where you had all the raw data in one of the columns, then that would be one where you would use with data, right? You'd copy the data into StatCrunch and then you use with data. But that's not what we're going to have here. And then just like with proportions, if you had to do the test with the rejection region, you could use StatCrunch for that, because the thing that's called t-stat, which will be right next to the p-value, it's the test statistic. So you wouldn't actually have to do the algebra to get the test statistic. You might have to figure out what the cutoff would be for the rejection region, but the test statistic, if you know where to look, you can make StatCrunch do it for you. All right, so starting off with the examples. So physician claims that a jogger's maximal oxygen uptake is greater than the average of all adults. Sample of 53 joggers had a mean of 38.7 milliliters per kilogram, standard deviation of 6. And then suppose the average of all adults is 36.5, and we want to perform a hypothesis test using the conventional significance level of 0.05 to see if there's evidence supporting the physician claim. So the physician's claim, if we go up toward the top, greater than the average of all adults. So that greater than tells us what we got to do with our alternative hypothesis. So if we're going to write our hypotheses out, the greater than tells us that our alternative should be mu greater than what it is for all adults, and we're supposing that that's 36 and a half, because that's right there in that second paragraph right at the beginning. Right, so right there, that's our mu 0. All right, and then our null is going to be that mu is equal to 36 and a half, right? If you back solve for the null, just put an equal sign in there. Let's see, then our summary values, I guess we can put them in. I guess I'll just make like little barriers here for all this stuff. So our summary values, we can actually see them in the first paragraph. Sample of 53 joggers, so n must be 53. And from that sample of 53 joggers, we get a mean of 38.7. Since that's the mean of the joggers in the sample, that's x bar, right? That's going to be a sample mean, that 38.7. And then the sample standard deviation is 6. Okay. Then we should be able to get the p-value. So let's see, if we go to StatCrunch, and we want to go to stat, then t-stats, one sample with summary. Sample mean was 38.7, sample standard deviation 6, sample size is 53, and then the null is that mu is equal to 36 and a half, and then the alternative has a greater than in it, and we should be good to go. So if we compute, there we are. So our p-value at the end of that table, 0.0051, and just like in 8.2, because we're going to do it the long way later, we're going to have that thought bubble with that test statistic in there, that 2.669. So, all right, let's see. Our p-value, so this is the part from StatCrunch. So the p-value ends up being 0.0051. And then we're going to have our little thought bubble saying that the test statistic is going to be 2.669. So I'll put that inside the cloud. All right. So then we're going to make a decision about the null. Well, just like before, I mean, this part works the same way. Even though it's about a mean instead of proportion, it's still, you compare the p-value to alpha, and if the p-value is smaller, then you're going to reject the null. Here, the p-value is smaller, so we are going to reject the null, right? Since 0.0051 is less than 0.05, so that would mean that the p-value is less than alpha, which would mean that the null should be rejected, right? Because when you have a p-value less than alpha, that's when you got a statistically significant result, so you should be rejecting the null. And then for the conclusion, let's see. So I guess we'll say that there is sufficient evidence or enough evidence to conclude what's in the alternative, and just having the alternative written in words. So we'll say that there is sufficient evidence to conclude that, and most of it is actually in the very first sentence up toward the top, and I'm going to just basically copy that over, that joggers maximal volume oxygen uptake is greater than the average of all adults. All right, so that's the first one. And then the second one, let's see, the second one is going to be about pH. And also, as you would probably anticipate, it's going to be a two-sided alternative. So just like with the last ones with proportions, that we had the one that was one-sided and the one that was two-sided, we're going to keep that going. So let's see what we've got here. One water treatment plant has a target pH of 8.5, and the mean and standard deviation of 1 hour's test results based on a sample size of 25. Sample mean of 8.42, sample standard deviation of 0.16. This last part, it's probably not obvious why that's there. So like this thing here, that when graphed, the sample is unimodal and symmetric. So why does it say that? Because we've never had that before. The reason it says that is because of this. The sample size is less than 30, but not by very much. And if you have a sample size that's not quite 30, but you're getting there, if you look at the sample data and they look relatively normal, then you can say, okay, it looks like we're fine here. So unimodal and symmetric, right, with 25 data points, that's about as close to a bell curve as you're probably going to get, right? The thing that would be bad is if you had something that was like obviously right skewed instead of symmetric, that would be bad. Or if you had something that wasn't unimodal, right? Like if you had two humps, that doesn't look like a bell curve. So unimodal and symmetric, that's about the best that you can do, I think, with just 25 data points. But that's why that's in there. It's in there because the sample size isn't quite 30, so we can't just automatically say, big enough for the central limit theorem, let's go. If it's a little small like that, then you do want to just take a look at a graph of the sample and make sure it looks all right. Let's see. Then the other thing here is, oh, look, our alpha's different. So notice here alpha's 0.10, not 0.05, because it can change. So here it's going to change a little bit. All right, so let's see what we're looking for. We're looking for evidence that the mean pH of water at the plant is different than 8.5. So the thing we're looking for evidence of, as usual, that's going to be our alternative. Oops, I'm making a giant A. I didn't mean to do that. All right, so H subscript A. There we go. So we're looking for evidence that mu is different than 8.5. So mu not equal to 8.5 when it's written symbolically. And then the null would kind of look like that, just with an equal sign in it. So mu equals 8.5. And let's see, then the next thing is, what's our sample data? Well, we know n's 25. We were just talking about that. And then the other values are kind of right after it. So based on 25 water samples, so n is 25. And then it says right in the wording that x bar is 8.42, and then s is 0.16. So we're going to need those. And then if we go to StatCrunch, we can make StatCrunch give us the p-value. So stat, then t-stats, one sample summary. Sample mean is 8.42, sample standard deviation of 0.16, sample size of 25, and then in the null we have an 8.5, and we do have a two-sided alternative, so we're good to go. And then compute. There's our p-value of 0.0197, and our test statistic works out very well. It's actually a decimal that terminates. It's -2.5. All right, so going back here, and I guess this is the part that's usually in maroon. So the StatCrunch part, we had a p-value of 0.0197, and then the test statistic, so to keep in our thought bubble for later, it's -2.5. All right, so I guess then the next thing is, well, what should our conclusion be? I guess what decision are we going to make, and then what should our conclusion be? Having a bigger alpha doesn't really affect anything because the p-value is 0.0197. So 0.197 is less than 0.1. It also would have been less than 0.05, right? So if we kept the same old alpha, we would end up in the same place. But I changed it just to change it, since every once in a while you do get a different one. But the p-value is less than alpha, and that's the situation where you would have a statistically significant result. So that means that the null should be rejected. All right, and then as a formal conclusion, something like that there is sufficient evidence to conclude, and then we'll just put in what's in the alternative, but in words. So there is sufficient or enough evidence to conclude that. And then the alternative is actually right at the end of that second paragraph, that the mean pH of water at the plant is different than 8.5. Okay. We had enough to say that since our p-value is nice and small. And I kind of want to point out here too that this is one where maybe intuitively you wouldn't expect to reject the null because the sample mean is fairly close to it, right? It's 8.42. Doesn't feel like it's that far away from 8.5. And then the sample size isn't very big, but the sample standard deviation is really small. And that's why this is happening. Right, with that tiny little sample standard deviation, you don't get a lot of variation there. So because of that, the standard error is really little. Like when you have s over the square root of n, it's 0.16 divided by 5. Right? It's a little number. It's 0.032. And so, yeah, then that's 2.5 standard deviations away. Right? That 8.42 is going to be 2.5 standard deviations below 8.5. So it may not look intuitively like this is what we would end up with, but it's because that sample standard deviation is so small. All right, then the long way. Okay, so with the joggers, we already know what we're supposed to have for the hypotheses. Right, the null is that mu is equal to 36.5, and then the alternative is that mu is greater than 36.5. Let's see, what distribution should we use? Well, it's a mean, and anything with a mean, we should be using the t-distribution. But here we should use the t-distribution with 52 degrees of freedom. All right, so it's going to be students' t-distribution with 52 degrees of freedom. So why is it 52? It's 52 because n was 53, right? That's where this comes from. Right, n is 53, and generally the degrees of freedom is n minus 1. So 52. All right, well then if we're going to compute the test statistic, this is actually going to be shorter than it was for proportions. I suppose that's nice, right? It's a little bit shorter anyway. So we're going to have, so it's x bar minus mu 0 over s divided by the square root of n. And if you sub in, x bar is 38.7, right? We know that from before. Mu 0 is the value in the null, so it's 36.5. And then, let's see, sample standard deviation is 6. Sample size is 53, so the bottom should be 6 over the square root of 53. And then what you'll get here to 3 places is 2.669, which, if I scroll up for a second, there it is in the thought bubble, 2.669, same thing. All right, so then we get back down here, and then I guess just like before, it's going to be p-value here and on the left, and then the rejection region over here. And just like with 8.2, I want to do both of these just to get every possible path or every possible different look for how you could do the hypothesis test in here. But this distribution that's here, this would be the t-distribution with 52 degrees of freedom. And I guess that's also what it would be here. So the t-distribution with 52 df. And t-distributions are centered at 0, so when I draw this, that's what I'm going to put right in the center, I guess in both of these. And then we can get to the specifics here of the p-value and then the rejection region. Okay, so our test statistic is 2.669, so that's somewhere out to the right. Certainly it's bigger than 0. And then our p-value is just going to be a right tail because we have a greater than in the alternative hypothesis. So there's our p-value right there. And you could use the t-distribution within StatCrunch to do this. So if I go to Stat, Calculators, T, then I want 52 degrees of freedom, and then I want, let's see, I want a greater than or equal to, because I want a right tail, and my cutoff is 2.669. Compute that, 0051. Looks like that's what our p-value is. So p-value of 0051. Let's see, did it round off the same way before? Did it go to 4 places? Yeah, right there it is from before, 0051. You can see it in the maroon. All right. So same p-value that we got before. If you were going to use the rejection region approach, then let's see, the rejection region should just be on the right side because we have a greater than the alternative hypothesis. So it's just going to be one piece over here. So it's a one-sided alternative, so the size of the rejection region is just alpha, and here our alpha was 0.05. And then we need the cutoff, so then you would use the t-distribution with 52 degrees of freedom to do it, and we just have to say, well, now we want a 0.05 in the tail as the probability, and the cutoff is 1.675 if you're going to 3 places. All right, so change color, 1.675. And then the test statistic, it's way past that, right? So the test statistic is greater than 1.675. Since it's 2.669, right? That's definitely bigger. So that means that the test statistic is in the rejection region. So then the decision, same thing either way. The p-value is less than alpha, which we already know since we did it that way on the front page, or I guess on the last page. It's actually not the front page. But we already know the p-value is less than alpha. And then also, if you do it using the other approach, the test statistic is in the rejection region. And those are these scenarios where you have a statistically significant result and the null. That's a terrible looking H. Let me just go ahead and fix that. I'm sure it's clear what letter that's supposed to be, but that just looks horrible. The null should be rejected. There we go. All right, so there's that. There's that first one. And then the other one with the pH, we can also do that one the long way. And that's what we're going to do next. All right, so here we already know what the hypotheses are. The null is that mu is equal to 8.5, and the alternative is that mu is not equal to 8.5. What distribution are we going to use? Well, it's for a mean, so we need to use the t-distribution, and the sample size is 25, so 25 minus 1 is 24. There's your degrees of freedom. So we want to use students' t-distribution with 24 degrees of freedom. And the 24 degrees of freedom, that's the important thing, right? Because that varies from one problem to another since it's based on the sample size. But where that's coming from, it's that n is 25. Right, that's our sample size based on 25 water samples. You can see it right up there. And the degrees of freedom is n minus 1 generally. So yeah, should be 24. Okay, next, getting the test statistic. This was the one that worked out really nicely. We already know what it's going to be. It's going to be -2.5. But just to go through what the computation would look like if you subbed everything in. So you'd have x bar minus mu 0 over s over the square root of n. X bar, the sample mean, is 8.42. Mu 0, the value in the null, is 8.5. And then in the denominator, that's going to be 0.16 over the square root of 25. And then, yeah, you get negative 2.5, exactly negative 2.5. Okay, moving on to part D. Once again, I guess we can put the p-value on the left, and we'll put the rejection region approach on the right. And both of these curves are supposed to be a t-distribution with 24 degrees of freedom. So I guess I'll have to write it kind of off-centered here. So with 24 df, same thing over here, t dist with 24 df. Okay. And then t-distribution, by definition, no matter the degrees of freedom, will be centered at 0. Okay, well then our test statistic is negative 2.5. So then that's way over here in the left tail. So if there's negative 2.5, we are going to need the tail that bounds. But we have a two-sided alternative here. So we also need a tail on the right starting the same distance away from 0. So that means we need a tail on the right that starts at positive 2.5. And we need that. Okay. Then if we go to StatCrunch, we're going to need, let's see, I guess it would be this time 24 degrees of freedom. And let's see, I guess I could do this as an in-between. That might be easier. And it should be from negative 2.5 to positive 2.5. And the in-between is the part that you don't really want. So we want the two tails, and this is giving us sort of the complement of what we want. So we're getting 9803 in the middle. So 1 minus 9803 is what we're actually looking for. So the p-value would be 1 minus 0.9803, which is 0.0197, which is the same thing that we got when we made StatCrunch do all of it. Then the rejection region, since this is a two-sided alternative, you got to split the rejection region in half. So alpha is 0.1 this time, or if I scroll back up, there it is, right? Alpha is 0.1, so you want to put half of alpha into each tail, right? So here for the rejection region, alpha is 0.1, so we need alpha over 2, which is 0.05 in each tail. So that means I need a left tail with a 0.05 in it. So alpha over 2, which is 0.05. And then I need a right tail that's the exact same size. So I'm going to make a right tail over here that also has a 0.05 in it. So alpha over 2, which is 0.05, also in that tail. And so then we just have to figure out what the cutoffs are. I guess really we only need the lower cutoff in a way, because we already know the test statistic's negative, so it's not going to end up in the right tail. That's kind of impossible. But let's see. What we're going to need now is, I guess you could do it as if you wanted a 0.9 in the middle. And you'll get 1.711, negative 1.711. The other way to do it is maybe to specify, if you went back to the standard, just a 0.05 in the right tail is how I have it set up right now. Same thing, right? 1.711. So either way, what we're going to end up with, and I guess I need to change back to blue, we're going to have a cutoff of 1.711 up there, and negative 1.711 for the left tail. And then the test statistic is out in the tail, right? Like it's out here, it's less than negative 1.711. So out there you have your test statistic of negative 2.5. So it's in the rejection region. right? So for the decision about the null, well, the p-value is less than alpha, which we kind of already know that because when we had StatCrunch through everything 2 pages ago, that was what happened there. And then also the test statistic is in the rejection region, right? It's in the piece that's on the left side. And so these are the scenarios where you have a statistically significant result and the null should be rejected. All right, so a lot of the steps that you would use to do the hypothesis test stay the same, except that when it's for a mean, then you're going to use a t-distribution instead of a standard normal, right? Standard normal for proportion, t for mean. I guess then some of the computations are different. Like you're going to do all the computations like on this page and the page before, right? The test statistic looks a little bit different, even though it's still the same general idea. But a lot of what you would do in a hypothesis test generally just kind of fans out to the specific scenarios. Right, like the way that you set up hypotheses, it's always pretty much the same. Rather, I guess if it's a proportion or if it's a mean, right? You're looking for the same stuff. You're looking for what kind of inequality you're going to have in the alternative. And then if you have a two-sided alternative, you got to split the rejection region into 2 pieces, right? That always happens, regardless of if you're talking about a proportion or a mean. So there is a whole lot of stuff that does transfer from one type of hypothesis test to another, which is good because we're going to have 3 more of them. So it's good that there's that consistency. Otherwise, this would be an absolutely enormous amount of stuff. But I think that would pretty much cover it for this section, for section 8.3. And this page and the last page where everything's done the long way, you don't really have to do it that way because you could have StatCrunch do everything. Even with the rejection region approach, I guess there you might have to find the cutoff or cutoffs for the rejection region, but you could make StatCrunch give you the test statistic because it will, right? It'll show up within the output. You just have to know where it is. But I guess if you want to do it the long way, you can, but I would assume most people are going to use something like StatCrunch as much as they can. And I certainly wouldn't blame you, right? It cuts out the algebra, it makes everything faster, and you don't have to worry about algebra errors. That sounds like a pretty good deal. I would take it too. So anyway, I think that's everything for section 8.3.